Snehit, okay?
Yeah.
Yes, sir. Yes, sir. It's running.
Okay.
Recording is running.
Yeah.
So we have to enter the data. You know how to enter the data. So by dragging and dropping, we can enter the data. So I'm doing that because that is very easy. So, okay, we say yes. So we are using the first sheet, okay, where I wrote WN. And this we have to say as time series, yes. Time series forward. Then this monthly data from 1960 January forward. Apply. So we have certain these data sets. And I shall show you the parallelogram and also the unit test for some of these variables. So first let us consider WN. Go to the variable, we can have a time series plot. Morning I will show you this one, okay? So this is the time series plot. Definitely we know.
Sir, it was
This
monthly,
is
na?
a large number of.
Hello, sir.
Can you hear me?
Hello, sir.
And can you see?
Sir, in the option it was monthly, na?
What is it?
Sir, in the option in time series frequency, it was. It was monthly data.
Have you entered the data?
Yes, sir.
Then
Series
we go to
frequency
the
monthly.
variable. Monthly, right?
Then
Monthly.
Then I forwarded.
So in that case,
then
we
it
can
is
go to the data. Okay, I shall show you again. If we go to the data, here we have data set structure. That is this one. So we have the time series. Click forward. Then we click monthly. Okay. And,
Yes,
and then click forward. Right?
Yes, sir.
Then here I am taking the data from 1960 January. You can change it if you want. No time is recorded for this data set. So I am just using this one. And then we click forward and apply. So we get it. Is it clear?
Yes, sir.
Yeah. So we want to find the nature of the first variable, Wn. Go to the variable, we can have a time series flow. Click it. Here we have the time series flow. Stationary, large number of mean reversions. Okay. Now, to get the classical stationarity check, we go to the variable. Here we have parallelogram. So we click this parallelogram and we have to give the lab. By default, Gretl has taken 2 years, that is 24 lab for monthly data. Then we click OK. Okay. Clicking OK, we get 2 windows. One is the graph of ECF and PACF. And morning session we saw this one. All the autocorrelation coefficients and the partial autocorrelation coefficients are within the 95-degree confidence level.
Sir, we had the option
Yes.
in the parallelogram. Sir, use Bartlett's standard error. Sir, what is about that?
What is the?
Sir, you again run the parallelogram function from variable.
Parallelogram. Then click. Okay, I shall show you again. Go to the variable. First select the variable. Then go to the variable. Then we have correlogram. Click this one, correlogram. And then we have to enter the maximum lag.
Sir, it is selecting the maximum
Okay.
lag itself.
No, there is no rule for that.
Okay.
And
Sir,
maybe it is yeah, it is better we leave it to the computer.
okay, sir. Sir,
As I told you earlier, what is?
Sir, what is that extra option is there? Use Bartlett standard error. Sir, what is that?
Bartlett standard errors. Yeah, we have a test by Bartlett, and usually that is the standard error that we use. Bartlett standard error, and that is the case where we have a constant, whether we have a constant variance or not. That is the homoscedasticity assumption. We have a test by Bartlett. So if we are using a constant variance assumption, then we can use the Bartlett standard error. Anyway, it doesn't matter in this case. So
Okay,
either
sir.
we can use this one or otherwise, because the standard error is usually standard error of the confidence interval is given in terms of 1.96 divided by root t, where t, capital T, is the sample size.
Okay.
Okay. So if we click OK, then
query.
we get
The one
Eh?
query, Anita here.
What is
this lag, no? You said let the computer. If there is a change
Yeah.
in that, does it affect the results? Could you throw
No,
some?
no. The thing is, we are getting a sufficiently long picture of this. If we specify the lag as 15, we will get only this much. There will not be any change in the autocorrelation coefficients. Got the idea? We will get the same picture below 15 if we specify the lag as 15. Got the idea?
Okay.
The autocorrelation coefficients are not at all affected in estimation by changing the lag. Nothing. We will, for every lag, it is calculated. If we specify the lag as 10, the first 10 autocorrelation coefficients will be reported. If we specify the lag 15, then the first 15 autocorrelation coefficients are reported. There will not be any change. So this will remain the same.
Thank you.
You can try that.
Yes, sir. Thank you.
Yeah. So this is the graph. And here we have the values, ACF value and PACF value. There will not be any change in this ACF and PACF values with regard to the change of the lag, nothing. But the Q stat will change with the lag. That's the only case. This Q statistic is the statistic indicating whether the ACF and PACF, ACF together and PACF together are significant or not. In all these cases, this is not at all significant. That is, we do not have any significant spike. So that is given here. So this is the test I told you earlier. The statistical test on ACF and PACF, whether this is equal to 0 or not. So the null hypothesis is that the autocorrelation coefficient is equal to 0. So here the p-value is 0.688. We do not reject that null hypothesis. That means the autocorrelation coefficient is 0. This one is statistically 0. So all the autocorrelation coefficients within the 95% confidence interval are 0 statistically. Even though there are some values, they are statistically 0. That is it. Okay? Is it clear?
Yes, sir.
Okay.
Yeah. So So it is enough that we report the ACF and PACF. If any autocorrelation coefficient is above the confidence level, then that is if we have any significant spike that is different from zero statistically. So that is the case. Here, none of the autocorrelation coefficients is zero statistically. That means we have a white noise. This series represents a white noise because the autocorrelation, all the autocorrelation coefficients are zero. That is, autocorrelation is zero.
Sir,
Come on.
there is a question. Sir, here we can see that autocorrelation in lag 1 is significantly close to 0. And for all the cases, it will be subsequently equal to 0. But if there might be cases where lag 1 will be not equal to 0 significantly, and subsequently in lag 3 or 4, it can become 0. Sir, ACF, is it a
See-
Portman-Tew type test? That
See, in this Q statistic, Portman test, the first one will have a star. That means it is significant. All others will not have a star. They are all insignificant. And in that case, the series is not a white noise. It is a stationary series, however. It is a stationary series because we have fast decaying ACF. Got it?
yes, sir. Yes, sir.
Okay?
Yes,
Yeah.
sir.
Right. So,
Sir, just now you said fast ACF. Could you throw some light on it with some example if you could? That might help us.
which one?
Just now you were
No.
just now you were
What is
mentioning
it? Uh,
you were mentioning that
mentioning? Okay.
there's a
Ah.
white noise around, right?
This is a white noise. Yeah.
So if you were to interpret in financial terms, could you give an example? And also you said that this is decline, this is auto decaying, right?
No, in this case,
No, in the
in
data
this
part
case,
here.
yeah, in this case, there is no such thing. There is no autocorrelation. There is no partial autocorrelation. That is why we say that this series,
Okay.
the series for which we have this ACF and this PACF, that series is a white noise series. That is, that particular series has a zero mean, a constant variance, and the correlation is zero. That is why we say we have a white noise.
Okay.
White noise is an error term, that is a spherical error term. The spherical error term that is the general term in econometrics. But in time series, we call a spherical error as white noise.
Okay.
It has a flat spectral density. Flat spectral density means these three properties: zero mean, constant variance, zero autocovariance or autocorrelation.
Okay.
Got it?
Yes, sir. Thank you.
So anybody else, any doubt? So shall we go to the next one? Okay, I shall close this one. Then the second variable, go to the variable, then parallelogram. We are using 24. If we use only 20, then we will be getting up to 20 autocorrelation functions. That's all. 24 it will give us a sufficiently long view. So I'm clicking OK. So here we have the case. Now see, we have 3 significant spikes here. And these 3 significant spikes are given with the star here, ACF, 3 significant spikes. Also, we have some marginally significant one. These 2 are marginal. These 2 are marginal ones. And in PSCF, we have 1 significant spike that is given by this one, this star. And the last one, this, there is a marginal one. And here also there is a marginal. And see the Q statistic. The entire Q statistic is 0. The p-value is 0. Q stat is very high. P-value 0 means we are rejecting the null hypothesis that the autocorrelation function is 0. That means it is not 0. The autocorrelation function is not 0. If autocorrelation function were 0, then we would have a white noise. Here we do not have a white noise. Since the autocorrelation functions become 0 after the third lag, we have a structure of fast decaying ACF. And fast decaying ACF shows a stationary system. So we have a stationary system. The particular variable is stationary. Now, reading along with the ACF of fast decaying ACF, if we have a significant spike in PACF, then that is an indication that we have a stationary AR process. Stationary AR process.
Sir, hello, sir. Sir, can you please just repeat repeat this one? That ACF is 0, we have a white noise.
ACF is 0.
We then having a white noise process.
Yeah, of course, we have a white noise.
And if not, then
we have to see whether the ACF is fast decaying or not.
okay.
If we have significant spikes, we have to see whether the significant spikes are fast decaying or not. If they are fast decaying, then we have a stationary variable. If they are not fast decaying, then we have a non-stationary variable. So we have these 2 cases whenever we have significant spikes. It may be either a stationary one like this one and a non-stationary one in another case that I shall show you. Got it?
Yes, sir.
Yeah.
Sir,
So along with this, come on.
sir, can there be a significant spike in 10 lakh, 15 lakh? Maybe it is fast decaying, and then after the 15th lakh, there is a significant spike. It can happen. Then what do we conclude?
No, usually, no. Usually, you see that particular decay is because of the sample data. That is a sampling error. We have to see whether within some 6, 7, 8, or 9, 10, within that lag, we have fast decay. At least say we have monthly data. Then up to 12 we can consider. But if the known decay continues after 12, then no, we cannot consider that.
Thank you, sir.
Yeah. Now let us consider the another case, say ARI, this one, the 4th one. So in this case, we go to the variable and a parallelogram. We are giving 24 lag itself. Click OK. And here we are getting this one. So here the ACF, even after 24 lag, it is not becoming 0 statistically. So we can compare these two cases. In both the cases, this and this. In both the cases, we have significant spike. Here, the spikes are not decaying fast, but here the spikes are decaying. ACF is fast decay. Here the ACF is not decaying fast. So the first one is a stationary case. The second one is a non-stationary case. Okay. In the first case, with the stationary variable, ACF, fast decaying ACF, we have one significant spike. So this will be an AR1 process. This is an AR1 process, stationary AR1 process. But in the second case, for the second case where ACF is not fast decay or where it is slow, where it slowly decay, there we have one or two significant spikes. The significant spikes in this case will indicate the number of unit roots. The number of unit roots. So we have to interpret it this way. For a non-stationary series, PACF will indicate the number of unit roots or the order of integration. Here actually the order of integration is only one. But because of the sampling error we are getting, it can so happen sometimes. So in that case, what we have to do is, that is why earlier I told you the parallelogram is not very definitive in many respects. So we have to go for the unit root test. But in the case of the stationary variable, the significant spike in PACF will indicate, again, roughly, approximately, the order of the AR process. Order of the AR process. So that's the difference between these two. Okay? Is it okay? Right? So shall we take up the next one?
Sir,
Say, for example, that we can take up the third one.
hello, sir.
Okay? So,
Sir, sir, you said we need to go to the
Ah.
unit root test, but why we should be going to the unit root test? There is a problem in this case, traditional method. You said that in case of the stationary process, there is a fast decaying feature which is reflected in both the ACF and PACF case. But in case of non-stationary case, the ACF has a slow decaying, but the PACF is somehow showing a different picture, isn't that?
yeah, that is it.
And that is why we need to proceed with the unit root tests.
Yeah, yes. But again, remember the unit root test also is not enough. It is not sufficient. It will not identify a white noise process. It will identify only a unit root or no unit root, stationary or non-stationary. It will not identify a white noise. That's the difference. What the idea?
Yes,
But
yes.
the parallelogram will identify a white noise. Unit root test will not identify a white noise. Got it?
Therefore, we need to use both of them actually.
Yeah, that is why sometimes we will have to use both. That is, in model adequacy test, we assume that the residuals are white noise. So we have this conducting a unit root test will not give us sufficient proof for that. So we have to go for the parallelogram. We have to do the parallelogram for the
Yes.
model adequacy test.
Okay, sir.
Okay, right. Now let us take this third variable. Go to the variable, then parallelogram. 24 lakh, Okay. And here we have the case. So the first ACF is significant. Similarly, the PACF, the first one is significant. The second PACF is significant at 10% level, and here is another one also, a marginal significance. And we know the Q stats is all the Q stats are significant. That means the autocorrelation coefficients as a whole is not equal to 0. We have this significant spike. Now, given this particular picture, we can say that we have a stationary series because the ACF is like fast decay. And we can interpret that in PACF, we have a significant spike. So to that extent, we can think that this is an AR process. But actually the data relate to an MA process. So that is why we say that the finding out the degree of whether the degree of MA or AR process, or whether it is an AR process or an MA process, is very difficult. We have to estimate it and then find out. So this will not give a conclusive idea whether we have MA series or AR series. Actually, this particular series is generated as an MA series. But if we interpret ACF as fast decay and one significant spike in PACF, that shows that this series is an AR1 series. At the same time, we can also do the other way. We can say that the PACF is fast decay and there is one significant spike in ACF. Therefore, this is an MA process, MA1 process. So both the interpretations are there. Got the idea? That is why we say the AGMA estimation is actually a trial and error method. Graphically, we cannot find out the order of, or not only the order and nature of the data itself, whether it is AR or MA or AGMA and so on. So we have to do the estimation, and that also we have to start with the AR1, AR2, MA1, MA2, AGMA 11, AGMA 12, AGMA 21, a large number of combinations we have to see. So that is why this is said to be a trial and error method.
Sir,
Ah,
sir, a process to be called as a AR1 process, the ACF has to be fast decaying, and the PACF
for an AR
has to,
for AR process, for an now see, I shall explain. For an AR process, ACF fast decaying, then the number of significant spikes in PACF will tell us the order of AR process. Opposite is the case for MA process. For the MA process, PACF is fast decaying, and given that the number of significant spikes in ACF will give us the order of MA. Got it?
yes, sir.
Yeah. So anybody else? So shall we continue?
Sir, by using all the combinations of AR and MA, we have to ensure that they all are non-significant. It is white noise.
If If the autocorrelation functions are all insignificant, that is, we do not reject the null hypothesis of zero autocorrelation, then we have a white noise. Okay.
Sir,
Ah.
sir, for the order of the process, to find out the order of the process for moving average, we need to find the spikes in the ACF, isn't it?
Right, ACF.
Sir, spikes, should we consider only those spikes? Those are
That
basically
is the
going beyond,
significant
going beyond,
spikes.
okay, going beyond that
Going
threshold of,
beyond this 95% confidence interval.
okay, sir.
Okay.
Yes, sir.
Okay. Now, shall we go to unit root test? Let us see with the the series that we identified as white noise, then AR1, then MA1, and the other one, integrated series. Let us see what happens with the unit root test. Okay. So all these I shall now remove. Right. Now let us start with the first one that we identified as white noise. Go to the variable, and here we have the unit root test. We have augmented decoupled test. Usually this is the one that most of the econometricians prefer. So we click this one. Then, as I told you earlier, we have a number of different specifications. Here we have some criterion, AICTE information criterion, or BIC, or T statistic, and so on. Gretl prefers AIC, but usually most of the econometricians say that it is better we use BIC, because AIC is very stringent, very strict. But BIC is somewhat moderate. So that's why usually BIC is preferred. But anyway, let us give it to Gretl, the AIC. Now here, test without constant, with constant, then with constant and trend, with constant, trend, and a trend squared. This is an additional one by Gretl. Usually we have only the first three specifications. These three specifications. Without constant, with the constant, and with the constant and trend. And in the null hypothesis, if we specify these three cases, then we can find out whether we have. Now see one thing, if we include a constant and a trend, then if the particular series has a trend, then that will be detrended. And we are checking for the unique roots on a detrended series. That is why we are using this trend. Okay, this we have already seen. If we include a trend in the regression equation, then that will detrend the entire series. So that is why we are using this. Actually, what we have to do is, it is better that we graph the particular series and see whether there is any trend or not. If there is no trend at all, then we can test the series without constant. The first one only. This with the constant also includes actually a trending a trend, because that actually that trend is the stochastic trend. Here we will have a stochastic trend and a deterministic trend. We will remove both the stochastic trend. So here we will have a trend. So if there is no trend at all visible, then it is better that we take only this one. But usually the Puritan statisticians say that all these three cases we have to do, and it is better that we get for all the three the same result. For all the three, the same result. We have already seen the time series plot of the white noise, and there is no trend at all. So maybe it is better that we test without constant. But remember, when we report it, it is better to report all the three cases. The last one we can just ignore, because that is an innovation by Gretl. There is no static idea behind that. Actually, under the null hypothesis, all these will have some different specifications, different interpretations. It's a little confusing one. If you read that working paper, the tradition is questioned. I have given those interpretations, I think maybe in some footnote. So it is better that you read that. So we will have some problems with all these under the null hypothesis. So that is why actually the Nelson Prosser, you remember the first uniroot testing. Nelson and Prosser did not use all these specifications. They used another specification which is called the Bhargava type of specification. And Bhargava type of specification will not have any problem of these three specifications under the null hypothesis. So I am referring you to that working paper. Okay, now anyway, let us use all the three in this case. And here we have two specifications: level of the variable and first difference of variable. These two cases we have to do whenever we do a uniroot testing for a particular one variable. First we have to do the level of variable. And if we find that there is a unit root in the level variable, then secondly we have to do this one, first difference of the variable. And if we find no unit root in the second case, first difference of the variable, then we can stop and we can say that there is one unit root. So it is non-stationary, it is an integrated variable of order 1, integrated process of order 1. But suppose the second case also we are rejecting, that is the first difference of the variable shows that there is another unit root. Then we have to go for the third test. For the third test means first we have to difference the variable and then we have to difference it again. That is the second difference. And that option is not given here. So we have to do it otherwise in Gretl. And we can do it. I shall show you how we do that. It is possible in Gretl to do that. Second difference. So we do the unit root test with the second difference. And if we find that there is no unit root, then we stop there. And we say that we have one, in this case, 1, 2, that is 2 unit roots. If again in the second difference we found a unit root, then again we have to differentiate and see whether there is a unit root in the third difference variable. And so this procedure we have to continue till we find that a particular section, the particular stage, there is no unit root. Then we can stop. So whenever we have the result of no unit root, then we stop. whether it is at the level variable or first difference or second difference and so on. If there is no unit root, there we stop. So that is the procedure. Is it clear?
Sir,
Ah,
sir, I wanted to know something that, sir, about the three options that we have, the test without a constant, with constant, and then with constant and trend. Sir, the issue is what basically means like without a constant, that means there is no, that intercept term is not present over there. Is it like
yeah,
that?
right. Intercept is not there.
And with constant meant only the intercept is there, but the
Right.
data is not trending actually, no trend.
Yeah.
So, sir, we should shall we select those options after looking at the graph that we are having with us for
Yes,
analysis?
that is what I suggest. That is,
Okay, sir.
we look at the graph and see whether there is any trend. If there is
And
a
sir,
trend,
sir,
then we have to use the second two with constant and with the constant and trend. If there is no
okay,
trend, then test without constant.
sir,
But
the fourth
remember,
option
ah, ah, what is it?
with constant, trend, and trend squared. Sir, trend squared, is it
Yeah. These
is
two
it
cases, we have to. If there is a trend, then these two cases we have to. Because if we have a case with constant, then there will be a trend with that. Do you remember a random walk process with a constant? It is called a random walk with drift.
with
That
drift?
drift is a trend. Got the
That
idea?
UI term, that UI term.
Yeah, right. So with constant means it will generate a stochastic trend. So we will have a trend there. Even for a non-stationary random walk process. So this is, if there is a unit root, then this without constant means a random walk with no drift. And this is a random walk with drift. And this is a random walk with drift and deterministic trend. That is the case. Got the
So
idea?
trend squared is the deterministic trend.
Yeah,
Okay, sir, I got that.
yeah, right. So now let us click this OK. Click OK and we get the result. So the null hypothesis is given that is A equals 1. Okay, A equals 1 means there is a unique root. A is the coefficient. Okay, that particular coefficient. That is the root is equal to 1. So here, what we have to select is the penultimate in every section, the penultimate line. That is the last but one, this p value. So we select this p value. And here also we select this p value. And here also we select this p value. And we know that if the p value is less than 5%, then we will reject the null hypothesis. Okay. Now this p value we know E minus. E minus means 0. Here also E minus. And in this case, that is also E minus. So in all the three cases, the p value is 0. P value is 0. That is less than 5%. So we reject the null hypothesis of unique root. That means there is no unique root. If there is no unique root, then the series is stationary. Got the idea? Okay. Right? So have you got the result?
Sir,
And you are
sir, here
considering
the
that?
p-value is less than 0, isn't that?
Yeah,
Therefore,
not
we
less than
reject our
0.
null hypothesis.
This is less than 5%. The p-value is 0.
P-value is 0. That means we reject our
Yeah,
null hypothesis.
right.
Null hypothesis of unit root.
Unit root. Right.
That means the series is stationary.
Yeah, the series is stationary. Okay. We know that particular series is a white noise. Okay, it's a white noise. And the unit test cannot identify a white noise as such. It can identify it as only a stationary series, either stationary or non-stationary. That is the only case. Only the parallelogram will identify a white noise.
The white noise.
Unit test will not identify a white noise. We will get the information. The only information that we get is that it is stationary. That's all. Is it clear? Okay.
Yes, sir.
Sir,
Everybody?
sir, in order to estimate, the series has to be stationary. No, it is not necessary. It can be a white noise. So if the series is stationary, then we can go ahead and estimate it.
Yeah, of course. But remember, for the model adequacy test, okay, we know the residual must be a white noise. So just finding that it is stationary will not tell us that the model is adequate. That's the problem. That is, once we have got the residual from a regression and subjecting this to the unit root test will not tell us that the model is adequate. We have to see that either we have to do all those model adequacy tests, or we have to go for the parallelogram. Now again, remember, the parallelogram will tell us only about the autocorrelation. Okay, only about the autocorrelation. Whether there is heteroscedasticity, specification problem, and so on, arch effect, all those will not, the information of all those will not be obtained from that. That is parallelogram. So parallelogram itself is not enough. But parallelogram will identify a white noise in terms of the autocorrelation. That is no autocorrelation. So for the model adequacy test, we have to do all those model adequacy tests. In addition to that, of course, we can also show the parallelogram, but not the unit root test. Unit root test will tell us only the stationarity, not the white noise nature. Okay, got it?
Yes, sir.
Yeah. So somebody else was asking something? No, okay. Now let us go to the variable, the fourth variable. Okay, this I am removing. The fourth variable, ARI. So go to the variable unit root test, ADF. Of course, we are doing all the three. And then click OK. Use level of variable. So click OK. We get the result here. And see the p-value. What do we find?
All above 5% significance.
The
Yeah,
null
all
hypothesis
the
is
p values are
accepted
above
in all 3 cases.
5%. This one and this one and this one. So that means we are not rejecting the null hypothesis. That means there is a unique root. Now remember, we cannot stop here. We have to see whether the first differential series has another unique root. So we again go to the variable. The same ARI, go to the variable, unit root test, ADF. This time we do with the first difference. Okay, and then click OK. And we get this result.
In all the cases, now we have values less than 5%. That means reject our null hypothesis.
Values less than 5%. Okay, this is 0. This also is 0. And this is close the p-value here. The p-value here also it is 0. So less than 5%. Conventional one. So we reject the null hypothesis.
Now the series is
That means
stationary.
there is no there is no unique root. The first difference is stationary, I0. The level variable is I1. So we have one unique root. Here we can stop. Where we reject the null hypothesis of unit root, there we stop. That is why in the earlier case, white noise case, we found that we were rejecting the null hypothesis. So we stop there. So when we do the unit root test, we have to continue testing. And we will stop where we have a result like this. That is where we reject the null hypothesis. Is it clear?
Yes, sir.
Yeah, right. So that's all with the unit root test. Now I shall give you some idea about the AGMA estimation. Okay. For that purpose, suppose we are taking this variable, the sixth variable, AGMA. And then here we go to the model and see the univariate time series. Here we have the AGMA. Okay. So I told you earlier, fitting an AGMA model is a time-consuming trial and error method. Just a feel of that I shall give you by clicking this one. Click AGMA, and we have this case. So we have to enter the dependent variable, that is ARMA, this one. So we are including this one. We can set this as default. We are not including any regressives because we have a univariate thing. If we have an independent variable, we can include it here. In that case, we will get a new model called ARMAX, ARMAX, ARMAX model. That is ARMA model with or ARIMA model with X independent variable, X variable. That is ARMAX. Now, we have two types of ARMA here. One is non-seasonal. That is the annual data specific one without any seasonal effect. Non-seasonal AR or non-seasonal MA. Similarly, non-seasonal integration. Remember, we are modeling an ARIMA process. ARIMA process. ARIMA. I refers to the integration. So that means first we have to see whether our model ARMA has a unit root or not. Okay. Now, if we want to give some specific labs, then we can directly give. Usually we do not give because the AR and MA are referring to some labs. Then we have seasonal AR and seasonal integration and seasonal MA teams. So both non-seasonal and seasonal AGMA. If we have a annual data, then we need not be worried about the seasonal one. So only non-seasonal one we can consider. If we have high frequency data, quarterly or monthly or and so on, then we have to consider the seasonal tapes also. Now, see the whether it is an AR1 process or MA1 process or MA2, AR2, ARMA11, ARMA12, we do not know. So all these cases we have to estimate. Now we know that, or we have already seen that ARMA is a stationary process, because by the, you remember the parallelogram has shown that it is a stationary series. Anyway, let us see the unit root also. The classical method relies on parallelogram, but we can also do the unit root test. Go to the ADF. We are doing all the three, then click OK. So the p-value is 0 here, the p-value is 0 here, and the p-value here also is 0. So that means this is a stationary series. So that means there is in ARIMA model that I is equal to 0. So we go back to this one. First, let us model an ARIMA 1, 0, 0 with no seasonal one. Okay, so this is an ARIMA 1, 0, 0. Then we have a seasonal 1, 0, 0, 0. So let us click OK. And here we have the result. So this phi 1 is the autocorrelation coefficient, that is the AR1 coefficient, and it is highly significant. We have 3 stars. Now we have to, so the model is significant. We have to see whether this is adequate or not. So we have to go to the test. Only normality, autocorrelation, and arch are given for this model adequacy. So let us see the normality of residual. So the p-value is greater than 5%. That means it has a normal distribution. You remember this, right? The p-value must be greater than 0 in all the cases. Then our model is adequate. And here also we have this. And the test is reported here. Then second, we go to the autocorrelation. We are giving a lag of 12. Okay. So the p-value is 0.4034. So this is greater than 5%. That means there is no autocorrelation. Only one autocorrelation test is given, and that is the Lewin box Q statistic. You remember the Q statistic we obtained for our, along with our parallelogram. Okay, that is the Lewin box Q statistic. It's given Q star statistic, because there is another statistic called box Pierce Q statistic. This Lewin box Q star statistic modifies the small sample problem of the earlier Q statistic. So that is why this is used here. So I don't know whether this is reported here. The LM test also is reported here. Only the chi-square value is given here, 11.4875, not the p-value. So anyway, the chi-square value is sufficiently large. So the p-value will be not sufficiently large. Okay, so the p-value will be large. Then we have to do the arch. So arch 12 lag So here also the p-value is greater than 5%. There is no arch effect. So this model is adequate. So this model is adequate and significant. Okay. So we have to keep it aside and then go for another model. Go to the model, then univariate, AGMA. So the same case. Now we are including AR1 and MA1, that is ARMA 1-1. Now click OK. And
Sir?
we find that both the coefficients are significant. Okay, got the idea? If
Sir.
any coefficient is, what is it?
Sir, in the AR process, the number of spikes in the PACF lets us identify the order of the process. Sir, in AR and MA, sir, from the cologram, whether what would be we should be seeing to find the order of process in that case?
No, that is the problem. Whether the cologram says it is AR1 or AR2 or MA1 and MA2. See, I have shown you the cologram for a MA1 process, right?
Yes, sir.
And we were not able to identify whether it is an MA1 or AR1. So it can so happen with the sample data. And that is why we have to do the trial and error method. It's the AGMA modeling or Box-Jenkins methodology is purely judgmental. That is, we have to do a lot of running regression and then find out whether it is significant. If it is not significant, we discard it. If it is not adequate, we discard it. Then do it in another way. So this will go on. And then finally, among all the adequate and significant models, we select the model that has the minimum information criteria. Got the idea?
Okay, sir. Yes,
Yeah.
sir.
So that is why it is called a trial and error method. But with the Gretl, now, not earlier it was not enough. It was not possible. Now it is possible to automatically identify the order of the particular ARMA model. So that I shall show you later on. First I shall show you this one, the difficulty in modeling ARMA. But since we have the particular this new package, we can automatically find out the order and then we can come back to this ARMA model window and do it. And also some programs are available in terms of X12 and X13 ARMA from the American Statistical Bureau. So those are available with Gretl at the Gretl website. We can download it and install them. Then that will identify the order of the ARMA model. So that way also we can identify it. So this particular case I am taking just to show how difficult it was earlier to identify or estimate a particular ARMA model. Now, coming back to this, we find that this model is statistically significant. We have to see whether it is adequate or not. So we go to the test and do this normality of residual. So the p-value is 0.61, that is greater than 5%. So there is normality assumption satisfied. Then again we go to the test and autocorrelation. A lag 12, okay. And the p-value is 0.635 or 636. So greater than 5%, there is no problem of autocorrelation. Go to the test, arch, 12 lag, okay. And here also the p-value is greater than 5%. That means this model also is adequate. Now, similarly, we can have a large number of models, and then we will find out which model we have to select. Now, where we have the minimum information criterion, that model we will select. Now, I'm not going into the entire process. It will take a lot of time. You can try that. Rather, I will compare these two. Usually, as I told you earlier, it is the BIC that most of the econometricians prefer. That is this Schwarz criterion or Schwarz Bayesian information criterion. So here we have this. So for this model, it is 854. And in this model, it is 855. So considering the information criterion, this model is better than this model. What the idea? So we select the model selection is done based on the information criterion, where the information criterion is the least. So we select this one. And moreover, we have another criterion, that is the parsimony. Parsimony is also the law of parsimony also is called Occam's razor, giving that we have to select a particular model as simple as possible. If we can capture the entire information in the dataset by a model with one parameter, then instead of two parameters, as in this case, then we have to prefer this particular model with one parameter estimate. So that is the law of parsimony. So both the law of parsimony and the information criterion favor this particular model. So we select this model. Got it? What the idea? Now I shall show you the actual AGMA model for this one. We have taken only these two cases. Now to get the automatic AGMA model, we go to the model univariate time series, and here we have the automatic AGMA. Okay. Now one more thing I shall show you for this one. If we go to the variable, see, can you see this X12 AGMA analysis? Can you see this one? Right?
Yes, sir.
This is
a blob
I have not downloaded and installed this particular program. That's why this is not active. So this X12 AGMA analysis is the package given by American Statistical Bureau. And now instead of X12 AGMA, they have X13 AGMA. So all these X12 and the X13 are available in the Gretl website. So anyway, we have this particular one. So we go to the model univariate automatic AGMA and click this one. And we have this case. So we select the ARMA one and the all others. For the time being, I am keeping as such. And then I am clicking OK. And here we have the result. Here all the possible combinations are given for the AGMA specification. That is 100000. This is the one that we estimated earlier. Okay. Then 101000. All the possible are estimated here. And where we find, for example, this AICC, this AICTE information criterion, then BIC and the Hanan-Quinn criterion out of these three. And Gretl has added another one, AICC. This is much more stringent than the AIC one. So where we get a significant, highly significant model, we select that one. So in this case, the highly significant models are this 20000. That is this one. All the information criteria favor that. And whereas at a 5% significance level, we have this model 101,000. 831.522 is the value. Or here we have 831.439. And this value is less than this one. So we can select this one, this particular model.
Sir, 200 means AR2
What the idea?
or MA0 or what will you say?
This is the even though the data is from an ARMA 11 process, it actually ended up as an AR2 process. AR2 process. And remember, the law of parsimony favors both, whether AR11 or ARMA 11 or AR2, because we have two parameters to estimate. So out of these two, the information criterion favor ARMA 200, ARMA 200, this one. So now we can go back to that AGMA specification, and there we can give 200 and then estimate the particular node. What the idea? Is it clear? Because we have the co-integration process also. So shall I now turn to the co-integration process? Is it clear now?
Sir, can you please just go to that ARMA process and set 200 and see the results?
Yeah. See, we go to the model univariate AGMA. Then we have this model already. So here we have AR2, MA0. So we have 200,000. Now click OK. And we get this result. So both the coefficients are significant. And let us see this one, the most important one, normality, autocorrelation, arch. So let us see this one. So we have the normality assumption satisfied. Then autocorrelation, we have 12 lakh. The p-value is greater than 5%. Therefore, there is no problem. Then we have arch, 12 lakh. The p-value is 0.647, 0.47. There is no problem. So the model is adequate and significant. Got it?
Hello, sir.
Okay.
Sir, in the results, like both the two p-values are significant. Sir, here phi 1 and phi 2 is what is basically the regressors actually here.
See, this is an AR2 process. So in AR2 process, say by t is regressed on both by t minus 1 and by t minus 2. So the phi 1 is the coefficient of by t minus 1 and phi 2 is the coefficient of by t minus 2. So we have two coefficients. Got it? Those two coefficients are given as this one. Now in Gretl, remember, if we have a seasonal coefficient, then that seasonal AR will appear with a capital P, capital phi. Yeah.
Okay.
And the non-seasonal MA game will appear as theta. So we will have theta 1, theta 2 and so on. And the seasonal MA coefficient will appear with a capital T. Capital T. So remember that. Or for just an illustration, I shall show you this. Okay, we go to the model. univariate time series, AGMA, and I am putting this MA term 1 just for illustration. And it is seasonal AR1 and seasonal MA1. Okay. And then we are estimating this, clicking OK. And here we have the cases. Now see this 5152, small 5152 refers to the non-seasonal AR2. This capital PHI1, this is the seasonal AR. This small theta, T, small t, this is the non-seasonal MAT. This capital theta is the seasonal MAT. What idea?
Yes, sir.
Got it?
Hello, sir.
Ah,
Sir, phi 1 is
come
basically
on.
the non-seasonal AR term. If the phi
Yeah.
is a small p,
Small p, right?
and sir, if it is
These
capital
two.
P, it is a seasonal AR.
Capital P, this is seasonal AR.
Sir, in case of small p, it is yt minus 1. But if it is a seasonal AR, then in equation, what representation should we consider for that?
No, so you see, usually we will not give it in terms of the equation. Rather, we will write as ARIMA, then within brackets, in this case, we will have 2, 0, 1, okay. Then bracket close, then and again another bracket. When we write, and in this case, as we have AR, for AR, we have 1 again. So we have 1, then 0, 1. What idea?
Yes, sir.
So we will write ARIMA within brackets. Here we have ARIMA non-seasonal 2. So we will write ARIMA within brackets 2, 0, 1. Then close the bracket. Then the seasonal one within another bracket. Then we write 1, 0, 1. Right?
Okay, sir.
Yeah, that is how we write it. So is it okay?
Hello,
Right?
sir.
So,
In here we are basically writing ARIMA 201 2 for we are basically having two regressors, that is yt
yeah,
minus 1 and yt
2
minus
AR,
that is
yeah,
2, and
yeah.
for MA1, that is seasonal one, is we are writing 1. Sir, the middle
Yeah.
0 is representing what?
That 0 is integration, order of
Okay.
integration. We have ARIMA, right?
Yes.
That
The
middle
order
I is for integration, order of integration. Here the order of integration is 0 because we have a stationary series.
stationary series. Okay.
Yeah, ARIMA, I equals 0.
Okay. Okay.
Okay. So shall we turn to co-integration?
Yes, sir.
Okay. So everybody okay? I'm closing this. Now for co-integration, I am taking another sheet. That is our earlier consumption income inflation. Let us take that particular sheet. So we drag and drop and we say yes. Then the second sheet. income, consumption, inflation. Click OK. This also is a time series data. Click yes. Mark time series. Forward. Monthly
One
data.
small request,
Forward.
if you can just increase this window size, it will be helpful. Otherwise, it will be strange.
No, last time I showed you
Yes,
this.
yeah, you can
Font
just click on the top box so that we can see it in full size. If that's okay with you.
See, for example, see for apply. If we click here, maximize,
Yes.
it will, the font size is still the same.
Okay.
Font size is still the same. And I don't know how we will change
Zoom,
the
you can zoom a bit.
size in Gretl.
If that's possible. Zoom a bit on the, there is a, on to the right hand side corner, there is a zoom option which you can zoom in if possible.
There is, with the Gretl, it is not possible, I think, because I have tried a lot earlier. I haven't found any zoom here. And I am using a desktop, therefore I cannot, this is not a touch screen. That's the problem. Okay, so that is why I am using this other way, this way. Okay, we have entered the data, consumption, income, and inflation. We want to know whether there is co-integration among these three variables. Now we have to see whether all the three variables are of the same integration. I will, because we do not have enough time, I will consider only one variable, consumption. And actually all the three variables are non-stationary. That is, they are of I1, integrated of order 1. So let us go to the variable unit root test, ADF. So all the three we are considering. Okay, this already we know. So we are using the level of variable. Then click OK. And here we have the result. See the p-value. P-value here 0.379. Here it is 0.711. And here this is 0.08. Yeah, in all the cases we have greater than 5%. So we do not reject the null hypothesis of unit root. Now we cannot stop here. We have to go to the variable again, do the unit root test again on the difference variable, right? So click use first difference of variable and then click OK. And in this case, we find that in all the cases, the p-value is less than, a p-value is equal to 0, that is less than 5%. So we reject the null hypothesis and we can stop the testing here. Got it? Similarly, we can find the other two variables also as I1. I'm not going into that. I am directly going into the unit root test. And for that, we have to see the multivariate time series. Multivariate time series. Here we have the vector autocorrelation var, then var lag selection, vector error correction, then co-integration test. JJ test is given here as Johansson test. Actually, it is Johansson and Jusselius test. Then we have the single equation residual based Engel-Granger test, co-integration test. First, we will do this one, and then we will do the JJ test. So click this co-integration Engel-Granger test. Now we have to give a lab order for this estimation. In all the multivariate cases, we have to give a lab order. And remember, we will be doing the JJ test in the context of a VAR model, that is vector autoregression. Therefore, it is better that we find the optimum lag of the vector autoregression. So first we go to the model multivariate time series. Here we have the var log selection, vector autoregression log selection, and this optimum log we can do in our subsequent cases. So we click this one. The maximum log already selected is 24. We can keep it as such. The three variable that we are considering are consumption, income, and inflation. We enter that. All the three are the endogenous variable in the framework of a var model. That is the property of a var model. All the variables are endogenous variables. We can also include some exogenous variable, but usually it is not there. We can include a constant also, but note the trend and other size. As such, we are doing it, and we have found that there are no seasonal problems, so we don't want any seasonal dummies also. If we find that there is seasonality, then we have to use this seasonal dummies. Now with this we click OK, and if we do not know how to proceed, then Gretl says what to do. If there is a star with the information criteria, then that star refers to the optimum log. That is the asterisk below indicates the best. That is minimized values of the respective information criteria. So this is the minimum one. Minimum information criteria, and that is for log 2. So log 2 is the optimum log. Got the idea? So we select this optimum log, and this log we will include in other cases. So I am removing this one. So we go to the model, multivariate time series, co-integration, Engelgranger. Remember, in Engelgranger framework, residual based is anybody any doubt? Anybody?
No, sir, continue.
Okay. So remember the Engelgranger single equation residual based test is not in the var framework. Okay, vector autoregression framework. And then we can use some log, but it is better that we find an optimum log and then apply that log here also. So we click here and give an optimum log of 2. Optimal log of 2 and the variables to test. So we are testing with a constant. So all other options are available here, but we are not going with that. We are testing with a constant. And then we click OK. And here what the Gretl does is it will test the unit test of all the variables. Okay, that is, it will test for a unit root in consumption, testing for a unit root in income, then testing for a unit root in inflation, then the co-integrating regression, and then testing for a unit root in U hat. U hat is the residual. We have already tested the other cases, so we need not do this. So we consider only this. Here we have to see whether there is a unit root in residual U hat.
Excuse me, sir.
Come on.
Sir, is this study based on one variable study? Sir, why we are not including exogenous and endogenous both? Here, sir, is it not based on relationship between dependent and independent? Like,
No, we have a single.
Then how it is multivariate technique we are applying here, no?
See the Gretl is giving the co-integration test in that framework only. See, earlier actually there was no distinction between univariate analysis and multivariate analysis, multivariate econometrics in Gretl. All the models were given in type only in one title, that is time series. Now they have changed it. They have formed one for univariate analysis, another for multivariate analysis. And the co-integration is usually a multivariate analysis, a multivariate in a multivariate framework. That is why even though the Engel-Granger test is a single equation test, they are giving it along with the other one. Both the tests are given together. That is the only thing. Okay?
Yes, sir.
Yeah. So we are interested only in this case, whether there is a uniroot in the residual U hat or not. So we have the null hypothesis and we see the p-value. The p-value is 0.001488. That is close to 0. That is less than 5%. So we reject the null hypothesis. That means in the residual, there is no unit root. So the residuals are I0 stationary. If the residuals are I0, then the two variables, income and the three variables, all the three variables, okay? All the three variables are in a co-integrating framework. Now see here, the co-integrating equation is given in terms of consumption as a function of income and inflation. We have only one, we are considering only one equation. So that means if there is co-integration among all these three variables,
despite all the terrible things happening to you, you must stay strong and overcome it. What is not said, just stay strong, you should be.
hello? Okay. So even though this regression is in level variable, since there is a co-integration among the three variables, this particular regression is not spurious. This is a valid regression. This is the long-run relationship between consumption, income, and inflation. This equation we can take as such. There is no problem. So that is the case. Now, if we do not know how Gretl is reporting its research, we can read this one. It says that there is evidence for a co-integrating relationship if the uniroot hypothesis is not rejected for the individual variables and the uniroot hypothesis is rejected for the residuals you had from the co-integrating regression. Now remember, it is better that we first to do the uniroot test on all the variables and then come to this one. Now again remember, these days we do not go for the single equation residual based tests. So this is only for illustration that I have shown. The test that we these days everywhere reported is the JJ test, Johansen-Jusselius test. So I shall show you now how we do that. Okay, so this is only for illustration. Now to do the JJ test, we go to the model, multivariate time series, and here we have the Johansen. Click this one.
Sir, it is
Come
written
on.
that there is evidence for a co-integrating relationship if the unit root hypothesis is not rejected for the individual variables. That means the individual variable should contain a unit.
That is what we started earlier,
Yes.
right? All
Yes,
the
yes.
variables must be of the same order of integration.
Exactly. If we are not having a non-stationary data, we can differentiate, but therefore we will be just removing the long run coefficients.
Yeah,
We would not
long run
having the long
information. Long run information. We are missing
and
long run information.
exactly, and in the
By
second term,
difference.
we find that the unit root hypothesis is rejected for the
Yeah,
residual.
yeah.
That means the residual
That
series
means there
is
is co-integration. Okay?
Yes, sir.
Yeah. Now remember, don't go for the Engel-Granger test. Okay. Even if you have only two variables, go for the JJ test. Because the JJ test, the other one is an OLS test. JJ test is a maximum likelihood test, and that is more reliable than the earlier one. So it is better we do the JJ test. Now, for the JJ test, we have the endogenous variables as in a VAR framework, consumption, income, inflation, and we have to give the optimum lag that we have already found as 2. So we have to give the lag 2. Then we shall give the OK. Keep all other things the same. We need not change anything. Click OK. And we have the result here. It is very important to see how we interpret the result. As I have told you earlier, we have two types of tests in JJ test. That is a trace test and a maximum eigenvalue test. That is this L-max test. P-values are given, and that is good. So that we can easily find out whether we reject or not. Now remember, these are given as rank. Rank refers to the cointegrating vector. 0 means there is no cointegration. This 1 means there is one cointegrating equation. 2 means there are two cointegrating equations. So that is the case. We need not be bothered about the eigenvalue and other things. Only the p-value of the trace and maximum eigenvalue test. Sometimes there may be contradiction between these two tests. In such cases, Johansson and Vesalius prefer the maximum eigenvalue test. So we go by this one. Okay. Now, how do we interpret this particular result? First, we postulate our null hypothesis that there is no cointegration. That is 0 cointegration. There is no cointegration. And we see the p-value. In both the cases, the p-value is 0. That is less than 5%. So we are rejecting the null hypothesis of no cointegration. Good idea? We are rejecting that. If we reject, or if only we reject the null hypothesis, then only we need to go to the second line, second row. Since we reject this first row, we go to the second row. And here our null hypothesis is that we have one cointegrating equation. One cointegrating equation. And the p-value is again close to 0. This case. Both the cases. So we are rejecting these. So when we reject a particular null hypothesis or the row, we will go to the next row. So we go to the next row. The null hypothesis is that we have two cointegrating equations. Two cointegrating equations. See the p-value. P-value is greater than 5%. In this case also, p-value is greater than 5%. If we do not reject a particular row, then we stop there. So we stop here. Suppose we have one more variable, and we have a third, we have a fourth row here. 4 variable means 4 rows. But we are not rejecting this one, means we stop there, and we need not consider the remaining rows. So where we do not reject, there we stop. Suppose we do not reject the first row, so we stop there and say that there is no cointegration. There is no cointegration, and stop there and say there is no cointegration. That's all. What idea? Is it clear?
Yes, sir.
Yeah. Now we have a small sample corrected. One also, this is for small sample, but we have a large sample here. And in this case also we find that we are not rejecting at the last one. Okay. Now remember there is very important point in this case. Suppose we have three variables and we are rejecting the third. We are rejecting the third row also. Okay, it can so happen. Then what does it mean? It means that we have met some problems with our either with our unit root test or with the co-integration test. Because if we reject all the rows, that is if we reject for all the n cases, small n, that is the number of variables, all the number of variables, or we can use k, the number of variables. If we reject for all the k rows, that simply means that the variables that we use are stationary variables. Remember, all the variables are stationary variables. They are not non-stationary variables. And that means there were some mistakes in our unit root testing. Got the idea? So be very careful that at least your last row is not rejected. So there must be one row that we do not reject. If we have k variables, then there must be k minus 1 at most, k minus 1 co-integrating equation only, not k co-integrating equation. So that is the case. Got the idea? Is it clear? If it is not clear, now what I am going to do is I will take the first difference of all these three variables. Taking the first difference of all these three variables means they are all stationary variables. Then I will do the JJ test. Let us see what will happen. To get the first difference of these three variables, we mark all the three variables and go to add. Okay, go to add. And here we have first difference of selected variables. Now here see we can have the log of the variable square, then log first difference, log difference, seasonal difference, and so on. A large number of options are here. We want the first difference of the selected variables. Click that and we get the delta consumption, delta income, and delta inflation, the first difference of these three variables. Now these three variables are, we know they are stationary. Now I am going to the model multivariate time series, co-integration Johansson, and click that. Instead of these three variables, of course, we haven't done with the optimum lag, but I am still using the second lag, okay? And adding these three variables. And I am using the second lag. I think the second lag will be the optimum one. First, we have to do the var lag selection. Okay, anyway, I'm just assuming. Now click this OK and see the result. What we are getting. What do we find? Can you tell me?
Sir, all
What
of
is
these
happening?
three are rejected.
We are rejecting all the rows. All the p-values are 0. We are rejecting all the rows because the variables that we consider are stationary variables. So this should not happen with our sample data. So at least one non-rejection must be there. Otherwise, we will be in trouble. Actually, this point is very important, and I shall tell you one of my experiences. In one thesis, 3 analytical chapters were there, of course, with the financial data, with the financial data and this FDI, then inflation, exchange rate, and all those 3 analytical chapters. And the candidate has given the Johansson test. In all the 3 chapters, the Johansson test, all the rows were rejected. But he was nicely writing that there is co-integration. So yes, and so. He was writing it like that. In fact, in every chapter, he was also giving a little theory, and in that little theory, he has written that the number of co-integrating vector must be at the most k minus 1. The candidate, the poor candidate has not understood that particular theory, but he has copied it, pasted it, and whatever result he got, he represented in that report and wrote that there is co-integration. So it was a clear case of rejecting the thesis and asking for a revision. So remember, it can so happen. So be very careful. Be very careful and see at least one row is not rejected. What the idea? Otherwise, if you have a situation like this, then you say that the variables appear to be stationary by the Johannes JJ test. So there may be some problem with the sample data considered for unit root test or the unit root testing procedure. In unit root testing procedure, there was some mistake. What the idea? Is it clear?
Yes, sir.
So now I think, do we have time now?
We are running
We can
out of
have-
time because the time. Yeah.
Or
So,
we can have some discussion.
yeah, sir. We can have some discussion if any questions and all for 5 minutes.
Yeah. Okay.
Sir,
Hmm.
what about the interpretation regarding these eigenvalues or trace statistics?
No. No, this I see actually what is the eigenvalue? Any idea? See, this eigenvalue is the proportion of the variation. That is
Explained
variance.
by
Proportion of the variance of the data matrix. So the first eigenvalue will be the maximum. The second one will be the second maximum, and so on. This will decrease in order, eigenvalue. The JJ test is based on the eigenvalue. That's why the Gretl is reporting that eigenvalue also. Okay. Then
yes,
anything else?
Any questions? Because we are going to wind up this session. Yeah, if you have any questions, you can ask it right now.
So
Now,
therefore,
if
what
you have any doubts,
sir,
you,
sir,
okay, yeah.
sir, here the rank 2, that means the third factor is selected. That means order of 2 is selected, and the eigenvalue is 0.21475 over there. So what interpretation do we draw from here?
Which this case or the second case or the first one? The
No, sir, the
original
first
one.
one actually, the
The
actual
first
one.
one. Yeah.
Yes, sir.
We have an optimum lab order of 2. Because in the VAR, see, a VAR model is having an endogenous variable with as a function of its own past values and the past values of other endogenous variables. That is a VAR model. So if we have 3 variables, for example, the first equation, consumption, will be given in terms of its own past values and the past values of income and consumption. This is different from ARDL. In ARDL model, we will include the present value of the variable also. That we are not giving. We are giving on the right hand side only the lagged values. And then in the second equation, we will have three equations. In the second equation, income is given in terms of the lagged values of income and the lagged values of consumption and inflation. Similarly, we have the third variable, inflation, in terms of the lagged values of the other two variables. Now, how many lags? 2 lags. That is the optimum lag. So, consumption as a function of its own 2 lags and 2 lags of income and inflation. What I did? That is first equation. In the second equation, income as a function of its own 2 lags. Yeah, 2 lags, then 2 lags of consumption and 2 lags of inflation. So that will be the model. That is the VAR model. And because of this, every equation we can estimate using ONS, independent of each other. That is the beauty of VAR, and that is why the VAR became very, very popular. Because we can use ONS for every equation separately. Got it?
Yes, sir.
Yeah. So, anything else?
Anything else? Otherwise, we can go with the water tanks because VMP sir's 2-day session comes to an end. If you have no questions, we can go with the water tanks. Okay. So VMP sir's 2-day sessions comes to an end. Sir has taken 6 sessions during these 2 days, Monday and today. Monday began with econometrics, financial econometrics, and we had practice sessions. And today explained time series econometrics and afternoon practice sessions. The session was so excellent, like always. The time when I called sir for inviting to our workshop, I thought like sir won't agree because of the online program. I was biased that sir was more interested in offline rather than online workshops. Yeah. Anyway, sir was agreed and did the sessions extremely well. Sir can deliver lectures continuously for a period of 10 days. That is a fact. That kind of contents and resources is with him. I believe sir was so impressed with our participants. Session was so lively. Yeah.
Of course, it was very, very interestingly interactive.
Yeah. So lively were asked a lot of questions. We had very good discussions, especially Shantanu Ghosh. Shantanu Ghosh raised so many questions, was so expressive, and I would say these questions has created some enlightenment to the other participants also. Hope everyone was benefited out of these discussions. We will have more workshop on financial econometrics with VMPSR later. Here now time has reached to give thanks to Professor. I believe it is from the participants. I welcome Dr. Devi Prasad Satapathy, Assistant Professor, Centurion University of Technology and Management, Odisha, for the water tanks. He is a regular participant of our workshop and conference. Yes, I can
Sir,
hear.
can you hear me?
Yeah,
Thank you,
I
sir,
can hear.
for giving me this opportunity. I'm thankful to Vijayamohanan Pillai, sir, because he has taken very wonderful session from the day one. He has started with econometrics, then further go on stepwise to the financial econometrics. Then he has nicely explained the multiple regression, which was explained with all the assumptions. We took example of Gretl. I do rarely find some workshop they talked on theoretical assumptions, but sir has shown in Gretl all the assumptions, how we can make all the assumptions, then the validity of the model. That was nicely explained in that sessions with hands-ons. Then, sir, moving to the time series, again, he was explained very conceptually the part one in the morning session. I was to the session completely involved and it was explained nicely to the conceptual part of the time series. Then go on to the stationarity and non-stationarity of the series. Then again, he proved with his content of practical application in the Gretl. It's all of R and co-integration test and also along with the AGMA model. It's nicely planned session and wonderful session. Perhaps if the time permits, sir can also go ahead with the moving ahead. I am really impressed the kind of energy sir have. I think we and as a participant all are enlightened with this kind of knowledge. We hope Biju sir will conduct a much more session with us. And I'm thankful again on behalf of Department of Commerce and Kerala University. The participant has been gained a lot during the session. Thank you very much, sir. Have a wonderful day. Thank you.
Thank you.
Yes, over to Biju sir.
Yeah. Thank you, Dr. Biju, and thank you all the participants. Thank you all.
Thank you, sir. Thank you.
Am I audible?
Yes, sir.
Am I audible? Okay. Am I audible right now?
Yes, sir.
Yes, sir.
Okay. So tomorrow we will have Professor Gabriel Simon Tuttle, and he deals with applied research in finance. And welcome welcome to that session. So tomorrow we will begin 9:30, morning 9:30. Okay. Thank you all participants for the best support. Thank you all.
Thank you, sir.